All right, well, thank you for coming. Today I'm going to be talking about IPv6, and I guess unless you've been living under a rock, you've probably heard about it in the news, even in mainstream news, because officially at the top level we've run out of IPv4 addresses, which is what practically everyone's been using until now, and that's mainly because the original IPv4 address space was 32 bits, which is only 4 billion or whatever odd addresses, and the population of the planet is more than that. So, and I think June 8 or something has been declared World IPv6 Day, so I don't know what that means in practice. But I'm not going to talk about the sort of network engineering issues related to this. Someone actually said to me the other day what they thought the talk was about, and I think it really sums it up. It is for you to know what to say when your boss comes to your desk and says, "I've heard about this IPv6 thing, what are we doing about it?" Okay, so I sort of want to go into a little analogy for a moment. When I don't travel very much, but when I travel to North America or to Europe, I'm actually in fear of my life. And that's because you all drive on the wrong side of the road. And apparently, I think it was Sweden a few years ago, also used to drive the same as Australia on the left-hand side of the road. And to be consistent with the rest of Europe, they decided they needed to switch. And so they declared this day where the day before everyone's driving on the left, the next day everybody's driving on the right. I'm going to tell you right now, this is not going to happen with IPv6. There is not going to be a little changeover where all the IPv4 gets turned off. In fact, I think even the equipment that I'm running at home right now for my broadband connection is not IPv6 capable. So, okay, so what do we have to do about it? So today I'm going to give you a really brief cheat sheet, the basic things that you just need to know to get programs working with IPv6, the basic concepts and things. Then I'm going to talk about how ASIO is designed to support IPv6, so just the API classes for that support. And then I'm going to talk about how to write client-side programs and then how to write server-side programs. Okay, so I'm going to compare against IPv4, since I'm assuming most of you are familiar with IPv4 in some way. So first of all, the difference is IPv4, we have 32 bits for each address, and IPv6 is 128 bits. And I don't know what 2 to the 128 is, but it's big. The next thing is, okay, we all know and love the dotted decimal address.
Hey, that's my router.
I hacked it.
No, you didn't.
And okay, I guess yes, you know it's your router. You can remember it.
Can you
yes.
maybe enlarge the picture a bit?
I don't know. Can we?
It may have a zoom on the projector.
The previous usually.
Or
That's a focus. Let me.
Okay. And yeah, as you can remember your own router address, I think there's only 4 numbers in there. That's not too hard to remember. The IPv6 addresses are written out in hex format. I don't know. I'm not going to remember that.
Yeah.
But yes, there are these 8 2-byte pairs making up the address, and just written out in hexadecimal. Now, you are actually allowed to compress one run of zeros in an IPv6 address by just dropping it out and leaving the columns there, and I think they're trying to make them at least, within a local network you can maybe remember it if you're lucky. There is a standard representation for an endpoint. An endpoint being, in ASIO terms, it's an IPv address and a port number. The old style IPv4 is just address colon port, but because colons are actually used inside the IPv6 address, I think this actually came from HTTP originally. The address portion is enclosed in square brackets. Yep.
Port's still 16 bits?
Yes, ports are still 16 bits, yes.
Why didn't they use a dot?
Yeah.
For which one? Between the hex.
Either way.
Well, I don't know. I mean, I could guess maybe it's so you can tell which one you're supposed to be parsing. As soon as you read your colon, this is not IPv4.
This is not your father's IP address.
Well, at least they made one improvement, and that's the loopback address, which for IPv4, the 127.0.0.1, is now just colon 1. And that's because that thing I said where you get to drop a string of zeros, that's actually 0, 0, 0, 0, 7 zeros and then a 1. There's the counterpart for the any address, which if you're writing a server you're probably familiar with because it means you're listening on all of the interfaces in your host, and that for IPv4 is the all zeros. It's also all zeros for IPv6, but again is compressed. And on some platforms you may actually see it represented as 0, 0. I just assume that's an implementation detail. Okay, that's really in a nutshell there. There are more complicated things, but there's Wikipedia, that sort of thing. Okay, so in ASIO there's a few classes that together give you the IPv6 support, and there's a few underlying design principles here, and one is that most user code should not need to be aware of whether it's operating on IPv4 and IPv6. But because that necessarily entails an implementation dealing in alternately IPv4 or IPv6 addresses, I also did not want to impose any costs associated with new and delete. So what I've done is I take a variant approach. I mean, it's a very simple variant. It's just either IPv4 address or IPv6 address. Okay, so the classes that make up the API are arranged like they have this relationship. So usually when you're starting up some sort of program, a client program, you need to resolve some addresses from a domain name server, DNS, and that's what the resolver is for. And so the resolver in ASIO returns you a list of endpoints. It actually mirrors the POSIX getAddressInfo function, if you're familiar with that. So rather than just giving you a list of addresses, you pass in a host name and a service name or port number, and you get back a list of corresponding endpoints. And an endpoint is composed of three things. One is the protocol, and by that I mean IPv4 or IPv6, the address, and the 16-bit port number. Now, the protocol class is, in ASIO, it is, first of all, as a concept for a protocol, there's two concepts. There's protocol and internet protocol, and it's actually internet protocol that is relevant here. And there's two classes that implement the internet protocol concept, and those are the TCP and UDP classes, and they are value type objects that you can assign into, but you can only assign either, it only really has two possible values, and one is the value that represents IPv4 and the other that represents IPv6. But you can see once you've actually made that assignment, you can then use it when you create a socket, say, and at this point you're not aware of, you don't need to be aware anyway, of which variant that you're using. So this is just an alternative syntax for initializing the socket if you're not able to open it at its point of construction. You can also, if you do need to write some protocol specific code, you can compare protocol values to test for v4 or v6. The next component that makes up the endpoint, the address, most of the time you will be dealing in the protocol independent version, which is just ASIO IP address, and actually internally it contains each of the other types, address v4 and address v6. If you're dealing with an address in protocol independent form, normally what you're going to be doing is converting it from maybe a configuration file or a command line argument. So you're going to have it in string form, and so to do that you can just call the from string function and it will automatically determine whether or not it's a v4 or v6 address and construct the address appropriately. Then, I mean, if you want to do the opposite conversion, toString just converts into the dotted decimal or hex format. There are also some sort of pseudo constants for the well-known addresses like loopback and the any address. So if you do need to, in one part of the code, say I am explicitly specifying the IPv4 loopback, then that's the sort of approach you would take. But then once you've assigned it into the address objects, you no longer need to know which version it is. I've also, on user request for Boost 147, there are some new functions added to the address class, because the concepts of loopback and unspecified, and synonym for any, and multicast addresses apply equally to IPv4 and IPv6, so I've added these functions that you can use to test if you need certain behaviour based on whether it's one of those types of addresses. If you do need to deal in the specific address types, then what you can do is, given a address v4, you can just assign it into the generic address class. Alternatively, you can test and then extract the protocol specific address from the generic type. And obviously same thing for version 6. Okay, now if you do want to deal specifically in IPv6 addresses, then the from string will only accept the hex format address. And it's possible, I don't know, if you're writing a configuration file, although you may want to, in your program as a whole, deal in the generic address type, you want to require an IPv6 address in a certain place or something. In which case, if you use this from string conversion, then it will give you an error if it's not the correct format for that type. You can also, because there are times, particularly if you're receiving addresses out of some protocol coming off the wire, that you need to construct these addresses from the raw representation, which for IPv4 is the big endian 32-bit. And so for that you can construct it from an array of unsigned char. And so for the IPv6 address, that's a 16 element array. There's a 4-element array equivalent for the v4 address. And if you need to do the opposite conversion, yes, there's 2 bytes as well. And although I've never seen a use for this in practice, there is a facility for creating these things called v4 mapped addresses, and there's another one we'll see in a moment called v4 compatible addresses, and these are ways of representing IPv4 addresses in an IPv6 format. And so these classes give you a way to both test whether or not it is that class of address, and then make the conversion in either direction. And yes, so there's the v4 compatible equivalent. Okay, so we had those 3 components the protocol, the address and the port number. That's put together, as we saw, in the endpoint type, and there are separate endpoints for TCP and UDP. You can see the classes there, and when you use them, you generally use them in a completely protocol independent way. They're actually implemented using this template, so there's type defs for this type, and this is done so that if you do need to, there are additional internet protocols out there like ICMP, which ASIO does support natively, SCTP, I'm sure there are some others. If you do need to extend it, then this is the starting point for that. Now, when there are several ways to construct an endpoint. If you want to specify a listening endpoint, so an endpoint that is listening on the any address, if you like, of your local system, then you can either do that to say explicitly, I'm creating one for IP version 4 or for IP version 6, as shown in the top two lines here, and they're both using the same port number there. Alternatively, if you've already obtained your address, your protocol independent address object from somewhere, you can construct the endpoint in that way. And if you need to get the elements back out again, then there are the accessor functions that you can use. Okay, so particularly now that we're going to have to deal with these massive hex addresses, you're going to be using DNS. Okay, so that's what the resolver is for. So you give it a host name and you give it a service name or a port number. And if you're not familiar with the idea of a service name, that means something like HTTP or SMTP, which depends on the platform how it's configured, but somewhere there's probably a file that has a mapping between these names and the corresponding port numbers. So when you use a resolver, the first thing you need to do is construct a query for it. And so you supply the host name and service name as strings, and then you resolve it, and the resolve gives you an iterator as the return value, because of course domain name resolution can give you one or more, or zero more if it fails, responses for any given host name. And so the typical thing you'll then do is you'll iterate over that sequence of endpoints in some way. And when I come to the client, how to design the client programs, we'll see why that's important. And if you have a very specific use case, you can limit your queries to only return endpoints for IP version 4 or IP version 6 if you need to. Okay, the other thing you'll probably run into if you're doing any serious socket program is at some point you're going to be setting options on your sockets, like common ones for doing no delay and buffer sizes and whatever, but some of the standard socket options have identifiers that are specific to the IP protocol, the IP version. So they'll actually, if you're using the C socket API, you have to supply different flags depending on which protocol you're using. ASIO hides that away for you, so you only need to deal with the higher level conceptual socket option, and it will automatically apply the correct one for you underneath. So the example I've got here is there's a, well, for IPv4 it's traditionally called TTL, or time to live. For IPv6 it's called hops. So I've adopted the IPv6 name here. And so when you set that option internally, ASIO will go, oh, this socket is an IPv4 socket, I need to set the IP TTL option, or alternatively set the unicast hops option on the socket if it's an IPv6. Okay, well that's a really quick tour of the the API ASIO provides. Now I'm going to talk about how you should actually use it in practice if you want to be IP version independent. So if you're writing a client, there are these three principles that you should keep in mind as a general rule. So the first one is you want to keep as much of your program as possible independent of the IP protocol. The next thing is that although you can deal in the address objects if you want to, you should probably prefer just to work in endpoints. And finally, that this is very important if you're a client. When you do a resolve, you may get back a list of both IPv6 and IPv4 endpoints, but you may not have IPv6 routing capability from your system. So it's important that you try every endpoint you get until you find one that works. And so, yep.
Are the endpoints sorted in the way that v6 is first? So there's some RFC.
Okay, yeah, so the question is, are the endpoints sorted so that v6 is first? And the answer to that is generally yes. I'm not sure if that's a standard or not, but that...
Well, there's a recommendation.
It might just be a recommendation.
To adopt v6 as the first.
That's right, and I'll actually come back to that in a moment.
Okay.
Okay, so we saw this before when I had the resolver example. This is a TCP client, so we're using the TCP resolver to resolve an iterator representing the list of endpoints. Then what you need to do is write some logic a little bit like this. And so this is to attempt a connection to each of the endpoints. And here I'm just illustrating with the synchronous code, but the same principle applies if you're going to use the async connect function. So we start off at the beginning and until we reach the end, and while we have an error code. Because as soon as we have a successful connect, we want to say, that's it, we don't want to keep trying. So we just basically loop, closing any previous attempt and starting the next connection attempt in the loop. Now, this year, because I've decided to free myself up to actually make changes to the ASIO API, I've added a new helper function for this, ASIO Connect. So if you get to upgrade to Boost 147, then I'd actually recommend just doing it this way, because it's going to be such a common pattern moving forward that it deserves to be encapsulated. And so all this does is takes the iterator returned by the resolver and keeps trying until one is successful. Now there's a little cheat here, because the resolver iterators, the end iterator is a default constructed iterator. This particular overload of connect just assumes that whatever iterator type it's passed represents the end. But there are other overloads that you can pass a pair of iterators.
Is that just the acceptor connector pattern, the connector part of the acceptor connector pattern?
More or less, yeah. Okay, now this comes back to your question before. I mean, let's face it, even though we've run out of IPv4 addresses, probably for the foreseeable future, we're still going to be primarily using IPv4. And if you have the IPv6 addresses first, and you always try them first, then you're going to be making these attempts to connect that are always going to fail, your connections are always going to take longer, and so on. I think
that shouldn't take any time, because the local routing table should
it depends. It depends where the routing stops. It could be, like.
Well, I'm wondering whether anyone has really seen that.
I actually came across this idea on the PostgreSQL mailing list.
Oh, okay.
So, yes, I think out in the real world people have. So you could do something like this, where you actually copy the list of endpoints first into a vector or something, and then, so I've used a stable partition here to put the IPv4 addresses first. I deliberately use stable because it could be that the DNS resolution deliberately returned the addresses in a particular order, because some of them might be the preferred host for a particular host name. But after that, the connection proceeds pretty much as before, except this time it's using the vector iterator. And again, if you get to upgrade to Boost 147, you can just use this this helper function to do it for you.
Does resolve return an input iterator?
I think it's just a forward. So it's not an input iterator. You can store one at any point. It's not destructive in that way.
Oh, okay.
Okay, so if you're running a UDP client, UDP is a bit trickier though, because generally you are sending a datagram to a specific host or a group of hosts using a broadcast or multicast. So you don't really have the equivalent of trying each host until one works necessarily. So for that, you're more likely, I'd say, to be converting from an address as a string rather than a host name. So in this case, you can still use a resolver and specify numeric host, and if you specify that, then it prevents it from going off to the DNS server to resolve the host name. Saves a little bit of time. And then once you've done that, you've got the UDP endpoint that you can then use when you do a send to operation on any outbound datagrams. Alternatively, you could just go back to using the address class, as I showed earlier, and use the from string to convert directly from the string representation. And that obviously will not do any hostname resolution at all. What is appropriate for you really depends on the protocol that you're implementing, I guess. I think, in my experience, most of the UDP is involved configuration files with specific IP addresses being specified.
Could you go back to the previous slide just so I can compare?
So yeah, here we've got the constructing a resolver query with the. So that's host name usually. Okay, and on the other side we've got server programs. I know it's a little artificial. Often programs are both clients and servers. But so the principles here are a little different though, because we've got to consider where the server is going to be deployed. So we've got systems that have support for IPv4 and IPv6, and then we've got systems that are IPv4 only. Except that's not quite right. We've actually got systems that have IPv4 and IPv6 as dual stack, and that means that you can construct an IPv6 listener socket and acceptor, but then accept incoming connections from IPv4 clients directly. And then we have systems that are separate stacks, and what that means is that you can't mix and match the two. If you want to accept connections from IPv4 clients, you have to be listening on an IPv4 address, and similarly an IPv6 address to accept IPv6 clients. Now, I think most POSIX systems, I think POSIX actually mandates dual stack. Separate stacks, so prior to Windows Vista, I think, was all separate stacks, even when IPv6, so XP has IPv6 support, but it's a separate stack. And I think, I'm not sure about Vista, but definitely Windows 7 onwards has proper dual stack support. And of course, yeah, you've got older systems that are IPv4 only still. Sorry, that's still not quite right. We now have the possibility of dual stack systems where the system administrator has turned off dual stack support. So, for example, on Linux, there's a kernel configuration option to turn it off. So, this is quite complex. How can we write servers that can deal with all of these deployment conditions? Okay, so if you're running a TCP server, then you can make a choice based on this. You can either go with just having one acceptor, one listener, and in that case you can support dual stack, you can support IPv6 only, or you can support IPv4 only, or if you are willing to take the extra complexity, you can run two acceptors, and then be able to deploy your program to all types of environment. So the first one is probably the simplest, and that's where you just have a single acceptor and you construct it probably from a string in a configuration file. And actually most of the ASIO examples take this approach where the string comes in as a command line argument. So you can run your program with 0000 dotted decimal, and it will automatically start listening for IPv4, or you can use the IPv6 any address and it will automatically start listening for IPv6. If the application you are running is one where you can actually run multiple instances of the program, so there's no shared state, say, this is probably the best approach because it's the simplest approach. There's a variant on this where you actually run multiple single acceptors, where you, in a configuration file, you have a list of all the addresses you want the server to listen on, and you then dynamically create as many acceptors as there are addresses in that list. And I've used that myself, because that also gives you the flexibility of listening on a specific interface rather than any address. Okay, so the next thing, if you want to support dual stack systems, but you need to know whether you are actually you do have proper dual stack support, then what you can do is, after determining the endpoint that you're going to listen on, you can try to set this socket option here called v6 only to false. On POSIX systems, it's specified that it should default to false, but on, say, older Windows systems, it actually defaults to true because it's not possible for it to be false because it's a separate stack system. So that means that if you make this call, the fact that it fails tells your program that you are not on a dual stack system. So this is a way of testing at runtime what support you have. And then after that, yeah, you just continue as before. But we can use the same sort of technique. We'll see. Sorry, the same socket option in the two acceptors case. If you want to support all scenarios, so the first option here is to create your acceptors so that you will have one for IPv4 and one for IPv6, and the IPv6 one will disable the dual stack support. And so that all you need to do here is, when you construct two of the acceptors and then set that v6 only option to true, and then from then on no IPv4 clients will be handled through that acceptor. If you don't want to open two acceptors unless you have to, because I mean underneath there's a file descriptor, right? Perhaps you're in an environment where you're sensitive to resources being used, then you might write something like this, where instead of setting the v6 only option, we're getting the value v6 only. So we first create an acceptor for IP version 6, and then we get the value of v6 only. It fills it out in this variable up here, and then after that we can test whether or not it's been set to true or false to decide whether or not we also need to create the second acceptor for IPv4 connections. And there's an option 3, and I forgot about option 3. Okay, so what did I actually mean here? Right, so in this case what we're trying to do is set, after opening the IPv6 acceptor, we're trying to say that it's not v6 only, and then we get the value to determine whether or not we were successful in making that that call. You could also be testing the error code here, but I'm deliberately ignoring the error code so that I can just continue, because we're not actually handling it as an error case so much as we're just proceeding through normal logic flow. So we retrieve the v6 only option, and then if true, we need to create the second acceptor to listen for the IPv4 connections. So this code is probably the most flexible of all the options, and if you really do want to both minimize your resource usage and support all deployment options, then this is probably the way to go. But it's quite complex, so I would, unless you have a real need to do that, I would probably go for one of the earlier, simpler options. Now, UDP servers are actually fairly similar on the server side, so I'll just skip through it quickly. And here, again, we can create the socket so it's bound to an address specified as a string. And again, we can determine whether or not we're on a dual stack system by making this set option call to try and disable v6 only. And we have the same types of options as we did in the TCP case. So we can create two separate sockets for UDP v4 and v6. And in this case, we're always setting the v6 one to true, so we're going to always use two separate sockets. Actually, just out of interest, does anybody have a need for UDP over both IPv4 and IPv6? Anybody come across that? Because every use I've had on UDP has always been like just one, typically IPv4. So, and if we want to minimize resource usage again, then we can use the v6 only option to test whether or not the dual stack support is available and we need to run the second socket. And option 3, almost identical to the TCP case. Okay, and so that's basically it. So I suppose there's just the 3 rules of thumb that I'd want you to take away from that, and that's, first of all, that try to keep your code protocol independent as much as you can. I realise it's not always possible, and sort of as an admission, there are parts of ASIO where it's not possible, particularly if you're going to deal in multicast, and that's because I think I haven't sufficiently analysed the problem space to be able to write a proper API for it. Remember, if you're running a client, do try all your endpoints. I've often seen people comment on mailing lists or whatever that, oh yeah, you only need to do the first address that you get back. That's not true. Okay, if you don't go and do an NS lookup for something like google.com, you are definitely going to get back multiple addresses in the response. And finally, if you're writing a server, always consider the deployment environment. So if you know you're only going to deploy to single stack systems or dual stack systems or whatever, like if you have control over the system configuration, then take the easy way out. And that's it.
Does this also handle zero-conf situations where you don't do DNS lookup or, say, in the Apple world, bonjour?
I believe things like that are implemented on top of multicast.
Yeah.
You probably,
Right.
what you need to do is very similar to the UDP server approach, right? You'd be possibly opening up to 2 sockets depending on whether or not you have the 2 interfaces in your system, and then you need to send out your multicast announcements on both sockets possibly.
Can you do multicast with ASIO?
Yes, you can. Yes.
Okay.
The limitations of multicast and ASIO come from are actually mostly in the socket options. If you need to do things like subscribe to a multicast group on a specific interface. Unfortunately,
Oh,
IPv4 works in terms of address. IPv6 works in terms of interface index. So you actually subscribe on interface number 2 or something like that. So there's a little bit of a disconnect there that I haven't yet found the appropriate abstraction for.
Okay.
I know that with privacy extensions you occasionally get new addresses on your net interface. Does that affect servers in some way, or is just that
Okay,
address
so
that you
does
bound to with
dynamic-
your socket kept alive?
Right, so does dynamic address
Yeah.
changes affect this? I think if you are using the any addresses, then you should be fine.
Oh, okay.
Okay, if you end up using, say, the first approach
So
and
you shouldn't resolve your own address because then
you shouldn't resolve your own address. Well, there are actually sometimes good reasons for listening on a specific interface rather than all interfaces. So, yeah, it's not a blanket rule, I guess. It depends on the sort of system you're deploying on. Okay, any more questions? Okay, well, thank you very much.